Okay, this is a fun example problem to do to combine a couple of the ideas we've got. Here I've got an apparatus which I'll call a projectile shooter. And in this apparatus it is two metal rails attached with a power supply. That's this one and this one, metal rails attached with a power supply. And then there's a movable metal bar on top. So let me undo those. So this movable metal bar can move up or down, sliding on those rails. Oops, okay. So let me give you some parameters. The magnetic field, we can put a constant magnetic field on it and we can make it into or out of the board. Currently I have it drawn in just because I tend to, that's easier to draw those little X's and circles than dots and circles. But anyway, it can be in or out. The whole apparatus has a electrical resistance of R, and we don't have to draw the resistor anywhere in particular, but I've drawn it just showing that it has an electrical resistance of R. The two rails are separated by L, and the projectile itself, right, the darker one that slides on the rails, can move a distance d before it leaves the rails. So let's say we want to ask, first of all, we're going to ask some questions about this. So again, because of the power, let's just make sure we understand that because of the power supply, we can send a current through there, and so then we can have a current, because, I didn't say explicitly that this bar across the top is a conductor that is in conduction with the rails. It's in contact, electrical conduction to the rails, so that this is a full loop, a full circuit. Okay. So the current goes through that. So there's a current going through the movable metal bar, that is the black one, and that current, which is in the magnetic field, feels a magnetic force, and again can go therefore either that way or that way. So the first question I have is, what should the direction of the magnetic field be if what's pictured is the correct direction of potential difference of battery? What direction should the current be? What direction should the magnetic field be if the current is in the direction as shown? What direction should the magnetic field be in order to make the bar move to the right? Okay, so we want the magnetic force on the bar to be in that direction. So the first question is be in or out to make force in direction shown. So that's the first question. So then we're going to say the given quantities, the things that we're going to set is for a given magnetic field, for a given distance to the end, for a given L separation between the two, for a given R resistance, what delta V should I set in order to have the object leave the projectile shooter at a speed of V. And I'm just using letters instead of numbers, but we could say, we have a 1 Tesla magnetic field, and the rails are 1 meter long. The separation between the rails is 10 centimeters. The resistance of the system is 15 ohms. What potential difference should I set so that the black metal bar leaves the projectile apparatus with a speed of 50 meters per second, right? And so we're just asking, what should we set delta V to be in order to get that speed? Okay, so we're just looking for relationships between these variables with all these as a given, solving for the relationships between all these variables, and then just solving for delta V, the voltage, or potential difference, I should say. First thing is, let's just answer part A. Part A is just a straightforward right-hand rule. So if the current goes in the direction shown, right, by the blue arrows. So the current through the rail is going sort of down the page, and I rotate that let's just use the inward field that we've got right now. So I'm putting my fingers in the direction of the current, and I rotate my fingers into the page. Then my thumb points to the right, and so that's pushing in the correct direction. Let's just do the opposite. If the current is going down the page, but the magnetic field were coming out, I'd rotate my fingers up, right hand, and my thumb would point back to the left. So the correct direction of magnetic field is, what happened? The correct direction of magnetic field is B is into the page. Okay, by the right-hand rule. That's just by the right-hand rule. That gives you a force. That gives you a force to the right. I know I put it a little bit at an angle, but hopefully you get that. So now we're going to answer the question, what potential difference should I set up in order to get this thing to have a certain speed? There are two ways to do this. We can do it from an energy point of view, or we can do it from a Newton's second law point of view. Most of you are going to want to do it from a Newton's second law point of view, but the easier way to do it is the energy point of view. From a Newton's second law point of view, if we found what FB was, then we could say, I got to give you the mass of the rail. I forgot to give you the mass of the rail. That's another given. Of course, because of F equals ma. So if we figured out the magnetic force, we could relate it to the acceleration, and we know that the acceleration is acceleration is related to the distance by this formula, and we can combine these to find the force. But it's and I mean I can do that. I can say A equals v squared. V initial is 0, starts from rest. So v squared over 2d. I can go ahead and plug that back in there and say that the magnetic force must be mv squared over 2d. I guess this was easy enough to do. And then say, okay, so that's in order to get a certain velocity, that's the force needed, right? That's how we figured out what the force was needed. F equals ma. So in order to get a certain velocity, we related velocity to the acceleration to the force. Okay, but we know that the force is IL cross B. The force on a current-carrying wire, or in this case current-carrying rod, in a magnetic field is IL cross B. And so therefore, once we find the force, we can find the current, because this is I and L, the length. It doesn't matter what the length of the rod is, it matters what the length is through which the current goes. And the current only goes through a distance L. So that's L and B, and the angle between I and B is 90 degrees. So ILB sine theta is the force, which is, we already found through kinematics and Newton's second law, was mv squared over 2d. So therefore we can solve for current. I is equal to mv squared over 2d times LB. So that's the current. And then, but we don't know what the current is, so we can therefore go ahead and say, but we do know delta V equals IR, right? Ohm's law. And so therefore, the potential difference must be the current times the resistance, which was given. And so the potential difference, I didn't leave myself much space, but mv squared R over 2d LB. So that's the potential difference. I guess that was easy enough with Newton's second law and kinematics. Newton's second law, kinematics, magnetic force on a current carrying wire, and Ohm's law, right? So we had to put together 4 different concepts here in order to solve this problem. We could also do it from an energy point of view. From an energy point of view, it's, find that a little easier, right? It's work equals change in kinetic energy. So the work done is the magnetic force times the distance that it goes. That's the work done, equals 1/2 mv squared. So, and therefore ILB is the force, times D is 1/2 mv squared. And so therefore I is equal to mv squared over 2 LBD. And so that's the current, and so therefore delta V, the potential difference, which is IR, is equal to mv squared R over 2 LBD. I better check those to see if they're the same. mv squared R over 2 LBD, yay! I got it right. Okay, so this was just another way. This was an energy way. This was the Newton's second law way. So with the energy way, it was the work energy theorem. It was the magnetic force on a current carrying wire, and Ohm's law. So 3 concepts here instead of 4 concepts. You should probably understand both of those, and I think that this is a good problem to solve. I did it quickly, but you can go back and you can go through it for yourself and try to do it. Let's just see what kind of numbers we're talking about here. Let's just think about a desktop setup. Just because some of you like numbers, just to see what kind of numbers we're talking here. Some kind of, let's just say, like I said, let's just give D equals 1 meter. The length of those rails is 1 meter. The separation between the rails, I just gave 10 centimeters. The magnetic field, let's say we could get a magnetic field of a Tesla. The resistance of the system is going to be pretty small, so we can talk about, I don't know, let's call it 10 ohms. I'm just giving round numbers here. And we said we want V. I just gave the number 50 meters per second. I'm just making up reasonable numbers for a desktop system. 50 meters per second would be a fast speed, right? This would be a dangerous projectile. D, B, L, V, and then the M of this rod, right? The rod is maybe 10 or 20 centimeters long. We'll call it, it could be a light metal, it could be a heavy metal. Let's call it 100 grams. So let's call mass equal to 0.1 kilograms. And so therefore, let's see what potential difference we would need. The potential difference is mass. I'm just going to plug in the numbers without you. I didn't even remember. I just chose kind of round numbers just to see what kind of size this would be for a desktop projectile apparatus. And by the way, it does assume no friction. I don't know if I said that. It assumes no friction between the moving piece and the rails, which we could reduce that friction pretty well. And so the number is, so that gives me 12.5 kilovolts. Again, it was all MKS units. I put it all in MKS units, so I didn't have to mess with my units. And so that gives me 12,500 volts, or 12.5 kilovolts. It's a high voltage, but we actually have power supplies in the lab that can get up to about 12,500 volts. Not much higher, but about that. So that's a reasonable lab experiment that we could do. So that would be a neat apparatus to try to build. If anybody, we do have to find something that gives us a 1 Tesla field, but we could do close to that with some of those permanent neodymium magnets. If we either scaled up the magnets or scaled down the size of the apparatus, this could be a fun thing to try. Okay, there you go. See you later. Just in case you were wondering, a railgun is a similar kind of apparatus, but not exactly what we were just discussing. It's a little bit more complicated, but a fun thing to think about if you like projectile apparati.